Okay, good morning and welcome back to the final part of my elliptic equation, namely the Laplace and Poisson equation. In the next couple of hours, we will be doing Green's function. We will introduce Green's function, Green's formula, and then Poisson kernel and Poisson kernel and Poisson formula in the case of upper half plane and balls, which we will use to establish some existence theorems. Okay. So, we will the first thing is that Green's formula, Green's theorem, Green's function, and representation formula. So, let us give you have already seen some representation. Let me recall a result which we have done few lectures back. If f is in CC2 of Rn, you already seen that the Ux equal to integral of phi is the fundamental solution f of y dy in Rn solves minus Laplacian of u equal to f. This we have given a complete proof. That is the beginning of the elliptic equations part. In some sense, converse is also true for bounded solution. Some sense, converse is also true that is true if n greater than or equal to 3. So, you have this theorem that is actually easy to prove. Theorem, if u tilde is a bounded solution of minus Laplacian of u equal to f, then where n greater than or equal to 3 we are assuming. I will tell you the reason, but that is an exercise which you can prove it. A bounded solution of minus Laplacian u equal to f, then u tilde has a representation. I am telling you u tilde is equal to some constant plus u, that means phi of x minus y f of y dy. You see, that means every bounded solution of this equation has this form. The proof is trivial due to proof is by Liouville's theorem, which we have seen already, Liouville's theorem. Because when n greater than or equal to 3, u is a bounded solution, u is a bounded solution. Okay. Yeah, this is only when, so your exercise is n equal to 2, u is not exercise, u is not bounded. You have to prove this actually. Of course, you have one information. The fundamental solution is bounded as mod x tends to infinity when n greater than or equal to 3, but then n equal to 2, the fundamental solution is not bounded. But a fundamental solution is not bounded is only one reason, but that does not mean that its integral is bounded. So, the exercise is you have to still use, you have to use the fact that the fundamental solution is not bounded at mod x tends to infinity, but then fundamental solutions are bounded functions when mod x. The singularity is at the origin, this is I am talking about that infinity. So, that is a fact which we are using it. So, once this is there, this implies u tilde minus u is bounded and harmonic in harmonic in Rn. So, you use Liouville's theorem to show that u tilde minus u is a constant. So, what this gives you, you already seen a kind of fundamental solution. So, now our aim is we want to study this equation minus Laplacian of u equal to f and in omega. So, you are studying this in domains now, maybe bounded domain u equal to g on d omega on d omega. So, you want to get a representation of your solution. So, you want to get if u is a solution, that is it, if u is a solution, that is what we call, these are all some a priori information solution, then you want to get write u in terms of f and g, in terms of f and g, that is what we are looking at a representation. But for that, if you look at it earlier, so what we are precisely looking, if you look at the previous case, this fundamental solution phi, you look at the fundamental solution phi which has a singularity, and that singularity, the information stored in that singularity what eventually used to prove this equation, if you recall. So, singularity will help you to get the equation. So, you need a function. So, you are looking for g, a two variable function x and y which has the same singularity, which has the same singularity as that of phi x minus y, as that of phi x minus y, but then you are working in bounded domain and you also want to write the boundary condition. So, you plus some boundary condition on g, we will come back to this again, some boundary condition. Okay. We will come that one. So, let us look at that one. So, we try to prove it that one. Okay. So, we have two equations, one equation is this one. So, you always call this is equation 1, and you also recall the equation corresponding to Laplacian. You have Laplacian phi x minus y, of course phi of x minus y, this is equal to 0, these are you have in, this is true in Rn minus x, keep that, use these two facts. So, you have other equation, this is the equation, we call it 2, we are using this. Now, we are going to apply Green's identities, Green's identities. Okay. So, but phi has a singularity. So, you choose y, so your y is in x and y are in omega. So, you have a domain omega, this is your domain omega, and you have a point here x here, and then it has a singularity there. So, I look at it, this can be 0 with respect to x or with respect to y. So, let me use with respect to y here, because I am fixing x here, it does not matter which one you fix it, I have to fix one. Okay. So, I have a point, so there is a singularity at that point. So, I put a small ball here, and that is of radius epsilon, I call this to be b epsilon of x, and this inside domain is your called b epsilon is nothing but omega minus b epsilon bar, that is outside domain. Okay. So, apply Green's identity, apply here u of y, I am doing it in v epsilon, u of y Laplacian of phi of everything with respect to y, x minus y minus phi of x minus y. I am applying Green's identity to u and phi, okay, and Laplacian of y with u of y. So, this is integrated, and then you have this is equal to by Green's identity with dv epsilon, not d omega, because your domain is that one. So, that will give you u d phi by d nu. Of course, nu is out external outward union. So, the nu will be in this direction here. For this, the nu will be in this direction. So, to be carefully choose what is that nu, okay. That is all you have to do. So, the y is here when you are integrating that part, this portion is fine. So, you have phi, of course, phi of x minus y du by d nu, okay. This is with respect to ds. Now, we want to understand this. Look at this first term, that we will come later. This is equal to 0 because phi has no singularity on this one. So, this equation and Laplacian y over uy is f. So, this whole thing will be equal to this thing. So, left hand side will be integral over minus phi of x minus y f of y dy. This is over b epsilon over dy. But this phi has a singularity, but that singularity is but it is locally integrable. So, you can apply some Lebesgue dominator convergence theorem or not, but if you want you can, yeah, f is replaced already by minus Laplacian is f. So, there is no psi here, okay. So, this if you want it, but that is a trivial thing from, you can write it here. If you want this, you can write chi v epsilon of y phi of x minus y f of y dy. So, if you have little smoothness, we are already assuming. So, you are assuming that u is a solution of that we already assumed. U is a smooth solution, C2 solution, that is what we will assume. So, assume that it has a solution, one has a solution, smooth solution, you are trying to derive this one, and you can apply because this will converge point wise to this quantity, and you can bounded by an integrable function because phi is integrable there, okay, omega. This will go to epsilon tends to 0 integral over omega phi of x minus y f of y dy. Okay. So, that is the left hand side is taken care of. Now, look at the right hand side. Right hand side it is dv epsilon. dv epsilon has two boundaries, one is d omega, one is db epsilon. But dealing with, I am telling you, what you have to do is that you have to make sure that your normal derivative is this one. So, we have 4 terms, 2 terms on the, there are 2 terms here, but the dv epsilon has 2 boundaries. So, totally there are 4 terms, 2 terms on d omega, that we will keep it as it is, you do not have to do anything because there is no epsilon, but then there are 2 terms on db epsilon. We want to analyze what will happen to the thing which you will do that, okay. You will okay. So, let us take care of one by one term. So, one term let me come right here, what you will get is phi of, I am taking one term phi minus x du by d nu, this is over d phi epsilon, sorry, this will be on db epsilon and ds. Now, look at this term, this is a bounded quantity, it is a smooth thing, and this we have already done in the beginning of the class, and this has an estimate. You can use this estimate on this small thing, and you know all this measure is 0, actually you can precisely write the estimate. I will leave it as an exercise here, what exactly will come, and then you can see that that goes to 0 as epsilon goes to 0. So, one epsilon term will go to 0. What about the other term? Other term is also you have worked out in the beginning. So, once more you work out d phi by d nu, this is over d b epsilon, and then you have your u now. Okay, this is with respect to y you are doing it x minus y, keep the parameters correctly. Okay. And this is u of y ds of y. And if you recall, and you would have gone through already my previous lectures, you can see that this is gives you the basically the measure of that. Okay. So, that exactly will go to the average, and this will go this exactly will be the average of u y as epsilon goes to 0, this you get it to go to u x. That is what the singularity which you have already done, this will go to 0 as epsilon tends to 0. So, combine your thing, you have the next one. So, you see the left hand side goes to this quantity, you keep it as it is, and then you have two terms on d omega, that also take it to the left hand side, and then one term on db epsilon goes to 0, the other term go to this term goes to u of x. So, we combine all these, if you get it. So, combining will give you u of x equal to integral of f of let me write phi first, phi of x minus y f of y dy, this is on omega minus you get d omega part phi of x minus d phi by d nu, nu with respect to y, because you are integrating y g of y ds, and there is one more boundary term, that is integral of okay, d omega and phi of x minus y and okay, du by d. Here u is replaced by g ds. Now, look at these terms. So, you have a representation, but this representation is good enough. Phi is known, f is known, g is known. So, you have to represent solution in this known. Okay. On the other hand, look at this, this is unknown, and not only it is an unknown, unknown in the normal derivative of u on the boundary, you can never impose that condition, because it is a boundary value problem, Dirichlet boundary value problem with u is already prescribed, you cannot prescribe any more condition on du by d nu. So, this is really an undesirable term, undesirable. So, here to the issue is that get rid of that, get rid of the last term. And how do you get rid of it? There are good motivation again to do that. How, if you look at how did we arrive at that this formula, you have applied your mean Green's identities for u and phi, both are Laplacian with phi having a singularity. That singularity of phi produced u. Okay. But now, if you look for so you have to add a corrector term to get a to get rid of the last term, you add a corrector term which should not have any singularity, but it should have the value exactly as phi. Okay. So, that motivates us to add a corrector term. So, we will do that. So, add a corrector term, add a corrector term, that is what we are doing it, corrector term. Okay. So, we will go to that one. So, fix x. So, you fix x. So, how do you add your character terms? To do that, okay, fix x in omega. So, you have to think fix x in omega, introduce phi x, introduce. So, you do not need any singularity what we are introducing. So, you introduce phi x is equal to phi x of y. It is not power, it is just a notation to represent my x, such that Laplacian of phi x, of course with respect to y, that should be 0. So, you need this is in omega, and then phi x equal to y equal to phi x of y minus y on d omega. Of course, this solvability is a question, because we do not know the solvability yet. So, we are assuming. So, this is I introduce, assume it, such a solution exists. Once you do that, now you apply again Green's identity, apply Green's identity to not think to u and phi x. The only difference from earlier thing is that phi had a singularity. So, you have to find a ball around it. Here you do not have to do it, this you can do it in omega, because there is no singularity. So, you can straight away apply the inequality and Laplacian phi equal to 0, follow that is not even need to follow, you just draw the inequality. So, you get this equation 0 is equal to, okay, phi x of y f of y dy, this is in omega, same term with phi of x minus y replaced by df by d nu y. This is our boundary of omega, g of y, this is ds, and then you will have exactly the term if you look at it here, you will have this boundary term. Instead of phi of x minus y, you will have phi x of y, but phi x of y is same as phi of x minus y, that is what we have used, okay. And d nu by is the last term is same as earlier. Okay. Now, subtract. Once you subtract, you get ux, okay. Ux equal to fy is common, earlier thing you have phi of x minus y. So, you are subtracting and introduce a new notation, I will say. So, it will be omega, you will have g of x y f of y dy, okay, and minus integral of d omega dg by d nu y, okay, of x by, this is not x minus y, okay, x y. Okay, I will tell you what is that one, g of y ds of y. This is what is called the Green's formula, Green's representation formula, Green's representation formula. So, please careful that since you get it, we are not solved with an equation. What we have done is that assuming that u is a solution, and then u satisfies this formula, that is all we have done it, nothing more than that. Okay. So, what is so g, what is g, where g of x y, where g of x y is equal to phi of x minus y minus phi x of y. So, what are its property? Indeed, both phi and phi x is is harmonic everywhere. This is harmonic except at y equal to x, and now phi and phi x is the same as the boundary. This implies Laplacian of y of g x y is equal to 0. So, it has the same singularity as that of phi omega minus x, and then you also have g is equal to 0 on d omega, right, x is fixed. So, g x dot equal to 0. In modern language, is solve this measure valued function minus Laplacian of g with respect to y equal to Dirac delta with g equal to 0 on d omega for each x dot. So, you see that is the modern language, which we will do that. Okay. So, that is what the Green's function. We will see more and more about the Green's function today. So, I want to make a remark, this is one important remark. Another important result I would like you to see, I will give you the hint here, but try to prove it. Okay. So, it is an exercise for you in this. Apparently, G is not symmetric. G apparently G does not look no, let me not write that, is apparently G does not look G is apparently it does not look like G is symmetric, because careful about that, G is symmetric. Okay. But the result tells you the proposition which you can prove. I would like you to prove it. Proposition tells you that g x y equal to g y x for all x y in omega with x not equal to 1. You see the way G is defined, you see the way G is defined is like that, and there is no, does not look like there is a symmetry. Of course, this is radial, so there is no issue, but this does not look like this, but it is true. So, let me give you the hint which you can use it to prove that one. You introduce V z equal to V z equal to G x z and W z is equal to G y z, fix x and y, fix x y x naught, everything in omega x not equal to y, and define that. Okay. And of course, so this is defined, so you have a domain omega, you have 2 points x and y. Now, take two small balls here, b epsilon of x, b epsilon y. So, apply Green's identity to V and W in this domain omega minus b epsilon bar of x union b epsilon of y bar to show V, to show what you want to do, to show V of y is equal to V of y is equal to, show that V of y is equal to, this is actually g x, but this is equal to, you show that this is equal to g y x, but then V of y is equal to g x y, which you will get g x y, you show this, and then you can also show that w z is equal to g x y, w x this is also equal to w of x. So, you can get all your results. So, we will stop this lecture here. So, what we are going to do is that we are going to construct Green's function for two special cases. So, the last remark in this lecture is that though once you find, so these are the steps. Once you get a Green's function, you have a Green's formula. So, even if you get a Green's function, you have a Green's formula, that does not mean that you can prove it. The x is u is indeed a solution, which you have to do it. So, getting a Green's function is one criteria, and then you have to show that the u defined by that formula well defined and satisfies the equation and solve the boundary value problem. That is not an easy thing. Secondly, obtaining g in general is as difficult as solving our problem of Laplacian of u given PDE, because to solve g you have to solve this phi x of y, right, you have to solve phi x, but solving phi x is again a boundary value problem, but then it is independent of given data f and g, that is the only thing difference from our problem. The data f and g are not coming, g is a kind of universal for f and g, the Green's function, it depends only on the operator. Okay. So, what we will do is that we construct Green's functions using some symmetry of the domain for the upper half space and the lower and the ball, use that to prove some existence theorems in the upper half space. That is the course of action in the next few lectures. Thank you.